Most people step over white quartz float without realizing it once carried gold, and in some places, still does. The deception lies in quartz's ubiquity. Milky quartz veins occur worldwide, and only a small fraction host precious metals. But even that small fraction accounts for some of the richest lode gold discoveries in history. The key is not the quartz itself, but the context in which it appears. A lone piece of white quartz in a creek may be nothing. The same piece near an iron-stained shear zone or greenstone contact may hint at something much more valuable. In hard rock environments, quartz veins form as mineral-rich fluids cool and precipitate out in cracks. If those fluids carried gold, it often settles out with the quartz, sometimes in visible flakes or strings, but more often invisibly bound to sulfides or trapped within the vein's microstructure. Gold's presence in quartz is rarely random. Hydrothermal systems, the geological engines that create auriferous quartz, tend to follow fault lines, contact zones, or ancient volcanic structures. So location isn't just helpful, it's essential. Many high-value gold deposits are spatially linked to greenstone belts or granite intrusions, and their quartz expressions look nearly identical to barren versions until tested. One of the most missed indicators is rusty red or orange iron oxide staining on quartz, especially along fracture lines. This isn't just superficial rust. It's often the weathered residue of iron sulfides like pyrite or arsenopyrite, which commonly carry gold. So while the untrained eye sees a dirty rock, the experienced prospector sees a chemical breadcrumb. Many of the richest gold veins ever discovered began with nothing more than a small outcrop of quartz with slight iron staining, overlooked for decades. The difference came down to knowing what subtle signs to recognize, and more importantly, where to look next. A dull white quartz vein might look worthless until you flip it over and catch a streak of red. That iron staining, ranging from a light blush to deep orange or brown, is often the first surface-level clue that the quartz once hosted, or still hosts, metallic minerals. Most miss this entirely, dismissing stained quartz as weathered or dirty, when in fact, it may be evidence of pyrite breakdown and a potential gold-bearing system. Iron oxides like limonite, goethite, or hematite form as sulfide minerals decay through weathering. If the original vein carried pyrite or arsenopyrite, both frequent gold companions, the resulting iron stains linger even after the sulfides have broken down. This staining tends to concentrate along hairline fractures or around the margins of the quartz, indicating fluid movement and chemical reaction zones. It's here, often invisible to the naked eye, that microscopic gold may remain trapped. These stains matter more when accompanied by other features. Quartz that is fractured, vuggy, containing small cavities, or sugary granular texture, holds more promise than massive, featureless chunks. Rust-colored halos or linear streaks in otherwise milky quartz often mean mineralization zones, places where fluids altered the rock chemically, potentially depositing gold in the process. Even small flecks of dark minerals within these stained zones warrant closer inspection. But iron staining alone isn't proof. It must be interpreted alongside host rock type, vein geometry, and regional history. For example, iron-stained quartz in a granitic terrain might mean nothing, while the same in a shear zone within a greenstone belt could be highly significant. It's the pattern, the way the stain cuts, pools, or follows microfractures, that reveals whether this is just surface oxidation or a sign of deeper mineralization. An effective field habit is to inspect quartz float or outcrop for hematitic crusts or yellow-brown coatings. Rub a piece on a hard white surface. If it leaves a yellowish streak, limonite is likely present. Combine that with a quick weight-in-hand feel, and you're already halfway to determining whether a sample deserves crushing or panning. Not all quartz veins signal the same gold potential, and one of the most overlooked distinctions lies in the vein structure itself. A single thick vein of brilliant white quartz may be striking in appearance, but ironically, it's often the less obvious, broken, or networked quartz that holds higher promise. This split between massive veins and stockwork zones can define the difference between a showy rock and a productive target. Massive quartz veins, often several feet wide and nearly featureless, were historically the focus of early hard rock mining. In some cases, such veins produced visible gold and supported profitable extraction. But these veins tend to pinch out or become barren with depth. Their uniformity, while visually dramatic, often works against them, lacking the complex fracture systems that allow gold-bearing fluids to circulate thoroughly. These monolithic veins also show less sulfide content and fewer signs of chemical alteration, both of which are necessary vectors for gold deposition. By contrast, stockwork quartz, consisting of a dense network of thin, cross-cutting veins, forms in zones of intense fracturing and fluid flow. These systems don't often produce visible gold on the surface, but they can contain finely disseminated gold locked in sulfide minerals across a broader volume. This makes them harder to identify casually, but potentially more economically viable. When gold is finely distributed in arsenopyrite or pyrite across a stockwork zone, modern processing techniques like flotation and cyanidation can recover it efficiently, even if it's invisible to the naked eye. Between these two extremes lies a third scenario: veinlet swarms, where several small quartz veins concentrate in a narrow corridor, often with iron staining or alteration halos in the host rock. These areas can act as feeders to larger systems or represent the final stages of hydrothermal activity, conditions known to concentrate gold. On the ground, this means adjusting your attention away from the biggest quartz chunks toward more fractured, interconnected systems. A hammer tap on a wall of quartz that breaks along iron-stained seams is more promising than a flawless white face. Equally important is noting the orientation of these veins. If they follow a consistent strike and dip, especially aligned with regional faulting, they're more likely to have acted as conduits for gold-bearing fluids. Many amateur prospectors fixate on the quartz and ignore the surrounding host rock, but in most productive systems, the host tells the real story. Quartz alone can form in almost any geologic setting, but gold-bearing quartz has a strong preference for specific rock types. Ignoring the matrix is like reading one word from a sentence and guessing the whole meaning. Greenstone belts, ancient volcanic sedimentary sequences rich in mafic and ultramafic rocks, are among the most reliable gold hosts globally. These belts, common in places like Western Australia, the Canadian Shield, and parts of Africa and Brazil, are known for structural deformation and chemical reactivity, both ideal for trapping gold. When quartz veins cut through altered basalt or schist, particularly if the host shows signs of shearing, chloridization, or carbonate flooding, the odds of gold increase dramatically. These alteration halos can be subtle, greenish, soft zones in otherwise hard rock, or dramatic with sulfide staining and disintegration. Intrusive contacts are another high potential setting. Where granites or diorites intrude older metamorphic sequences, the contact zone becomes a pressure release pathway for hydrothermal fluids. In such areas, you often find vein swarms, breccias, and alteration halos, all fertile ground for gold. Quartz veins in these zones may carry arsenopyrite or stibnite, key indicators of auriferous potential. In arid environments, weathered host rock can form caliche crusts or leave bleach zones around quartz exposures. These color shifts, white, tan, or rusty halos, often indicate chemical alteration zones where acidic fluids interacted with reactive host rock. This is especially true in volcanic terrains, where rhyolite and andesite serve as receptive host rocks for epithermal-style quartz gold veins. The structural context also matters. If the host rock shows signs of brittle failure, shears, fractures, or fault gouge, the quartz has had pathways for mineralized fluids. In the field, this often appears as fragmented, healed zones where multiple generations of quartz filled open space. Gold is frequently deposited in these late-stage fillings, particularly where the rock flexed during movement. In summary, a white quartz vein in granite might be a curiosity. The same vein in sheared greenstone, iron formation, or altered volcanic rock with limonite halos becomes a serious candidate. The host rock isn't just background. It's the chemistry, structure, and history that governs whether gold has any reason to be there. Glittering specks in quartz often trigger excitement, but unless you know what you're looking at, they can mislead as easily as they inform. Pyrite, or fool's gold, is frequently dismissed by newcomers, yet its presence in quartz veins is one of the most reliable indicators of nearby or encapsulated gold. The key is understanding not just the mineral, but its context. Pyrite Fs2, with its brassy yellow cubic crystals, is the most common iron sulfide found in quartz. It forms under the same hydrothermal conditions that deposit gold, and in many systems, the two co-precipitate. However, gold rarely sits on the surface of pyrite crystals. Instead, it can occur as submicroscopic inclusions inside the pyrite lattice or along fracture planes, meaning visual inspection isn't enough. Arsenopyrite Fs, a silver-gray sulfide with a metallic sheen, is even more telling. It forms at slightly higher temperatures and pressures, and is often more closely associated with high-grade gold zones in metamorphic terrains. In many mesothermal and orogenic gold systems, the ratio of pyrite to arsenopyrite gives clues about gold tenor. A quartz vein with 5–10% disseminated pyrite in a sheared greenstone host might carry sub-gram per ton gold. But if arsenopyrite dominates, especially with fine-grained textures or zoning, grades can spike above 10 GT. These are no longer speculative numbers. They're threshold values for modern economic extraction in underground settings. Visually, pyrite appears bright yellow with sharp edges and a hardness just below quartz. It won't flake or smear. Arsenopyrite, in contrast, has a steelier luster, more elongated crystals, and a faint garlic odor when struck or crushed, due to trace arsenic release. A cold metal rod pressed against a suspected arsenopyrite sample may pick up a faint scent on a warm day, offering a subtle field clue. Importantly, the presence of these sulfides alters how you handle the rock. Gold in pyrite or arsenopyrite is termed refractory. It won't respond to gravity separation or panning alone. Crushing and roasting, or flotation followed by chemical treatment, are often needed. But even in crude field terms, you can assess potential by observing how much sulfide remains in crushed concentrate. If you crush stained quartz, and the pan retains dense metallic sands that don't float or streak like mica, you're in business. The presence of gold in quartz is only half the battle. How that gold is bound determines everything from extraction method to profitability. This distinction between free milling and refractory gold often determines whether a rock sample becomes a saleable asset or a costly disappointment. Free milling gold is exactly what it sounds like, easily liberated by crushing and mechanical separation. In quartz, this usually appears as flakes, wires, or grains lodged in fractures or vugs, visible under magnification or, in rare cases, to the naked eye. These systems, often associated with epithermal or mesothermal quartz veins, allow simple recovery via gravity concentration, panning, sluicing, or centrifugal methods. Historic stamp mills and arrastras targeted these zones because the gold was accessible with little more than muscle and water. In field terms, free milling gold reveals itself in a few key ways. When quartz is crushed to sand and panned, specks of yellow metal that remain in the pan without floating, breaking, or oxidizing are likely gold. These particles will not streak or smear when rubbed. They remain malleable. A steel pin can dent or flatten them without shattering, unlike pyrite or mica. Free gold also feels disproportionately heavy when isolated, often sticking to the bottom of a pan even under heavy swirling. Refractory gold, on the other hand, is chemically or structurally locked within minerals, most commonly sulfides like pyrite or arsenopyrite. It won't pan out. You can crush quartz and see promising sulfide sands in the pan, but unless you process them further, no gold will be recovered. These systems require advanced techniques, roasting to oxidize sulfides, pressure oxidation, or chemical leaching like cyanidation. That added complexity doesn't make them worthless. Some of the world's highest grade deposits are refractory, but it means different handling and higher costs. Field recovery of refractory gold is more about recognizing potential than proving presence. If crushed quartz leaves behind a dense metallic concentrate that resists panning, and if that concentrate includes angular gray-white grains, arsenopyrite, or cubic brassy crystals, pyrite, the gold may be hidden inside. A quick test is to heat a speck of the concentrate over a flame on foil. If it turns reddish-brown iron oxide, sulfides are likely present, and so possibly is refractory gold. Knowing whether you're looking at a free milling or refractory system affects not only how you process the rock, but whether it's worth pursuing at all. For small-scale prospectors, free milling zones offer realistic recovery paths. Refractory systems demand either scale or partnership. Pick up enough quartz, and your hands develop a feel for weight that doesn't match volume. It's a crude but powerful field tool, especially when assessing whether quartz might carry gold or dense sulfides. Most quartz, even when bulky, feels deceptively light for its size. But introduce a meaningful load of pyrite, arsenopyrite, or native gold, and suddenly that same-sized rock seems to tug at your palm. Quartz itself has a specific gravity of around 2.65, which means most pieces feel like light gravel. Gold, by contrast, has a specific gravity of 19.3, nearly 8 times denser. Pyrite and arsenopyrite weigh in at about 5 and 6.1, respectively, both much heavier than quartz. When these minerals occur in veins or disseminated throughout the quartz matrix, the weight difference becomes surprisingly noticeable. The weight-in-hand test works best when comparing similar-sized samples. If you pick up 2 equally sized pieces of quartz from different outcrops, and one feels significantly heavier, it's likely carrying a higher load of metallic minerals, possibly gold or its sulfide proxies. Field geologists use this tactile metric routinely before committing to detailed testing. It doesn't confirm gold presence, but it flags anomalous density, often linked to mineralization. In seasoned hands, the trick becomes even more refined. A sample with significant sulfide content may also produce a faint clang when struck, a denser, sharper sound compared to the dull thud of barren quartz. In broken samples, metallic luster along fracture surfaces or the presence of brassy or silvery flecks that reflect light in a concentrated way can support the weight cue. You can further probe a suspect sample by crushing a small chip and panning the fines. If the pan retains dense material that clings to the bottom, resists being washed out, and displays either dull brassy glint sulfides or rich yellow sheen-free gold, that weight-in-hand instinct just found its proof. This method isn't infallible. Magnetite-bearing rocks, galena, or even some barite veins can also produce misleading density without any gold. But in known gold fields, especially where sulfide association is strong, an unusually heavy chunk of iron-stained quartz often means something is present worth investigating further. One of the simplest yet most revealing tools in a prospector's kit is a basic neodymium magnet. In quartz-hosted gold systems, a quick magnet sweep can help differentiate between sulfide types, rule out imposters, and even hint at deeper mineralization patterns. While gold itself is not magnetic, many of the minerals it associates with are, or at least respond to magnetism enough to warrant closer attention. Start with the sweep. Hold the magnet over a crushed or broken quartz sample, especially the iron-stained portions. If black or dark grains cling or twitch toward the magnet, you may be looking at magnetite or pyrite, both key indicators of hydrothermal systems. Magnetite, a strongly magnetic iron oxide, doesn't directly indicate gold, but its presence in quartz veins may point to a deeper mafic or ultramafic source rock, often favorable for gold. Pyrite, a weakly magnetic iron sulfide, frequently coexists with gold in skarn and greenstone-hosted deposits. A sluggish magnetic response in quartz concentrate can often be traced back to this mineral, especially when paired with arsenopyrite or chalcopyrite. The absence of magnetic response doesn't eliminate gold potential, but its presence adds a layer of plausibility, especially in regions known for iron sulfide gold systems. It's also a way to flag samples for follow-up crushing and concentrate tests. If you extract a dense, magnetic black sand from quartz, it's worth checking for fine gold laterally associated with those grains. Ultraviolet light, especially long-wave UV, is a more limited tool for gold prospecting, but it still has niche value. Most quartz fluoresces weakly or not at all, but certain gangue minerals in quartz veins like scheelite, a tungsten ore, or calcite can glow brightly. Scheelite fluoresces blue-white under shortwave UV and occasionally appears in gold quartz veins, especially in contact metamorphic settings. If your quartz sample glows in UV, it's likely not gold-related directly, but it tells you the vein system had complex fluid chemistry, sometimes a prerequisite for high-grade deposits. More importantly, UV can rule out glassy imposters. Man-made materials like slag, colored glass, or plastic will often fluoresce brightly and unrealistically. So if a shiny yellow inclusion in quartz glows green or blue under UV, odds are it's not gold. Real gold and sulfides remain inert under ultraviolet light, a silence that can be telling. Nothing bridges speculation and evidence like crushing a rock and watching gold settle in the pan. It's the oldest, most visceral proof in prospecting, and still one of the most revealing. Done correctly, field crushing and panning can expose free-milling gold, diagnose sulfide concentrations, and give a rough sense of grade. But doing it wrong can just as easily destroy delicate specks or bury gold in tailings. Start by choosing your sample wisely. Look for quartz with clear iron staining, sulfide inclusions, or that telltale weight in hand. Break the rock into manageable pieces using a hammer and safety glasses. Choose a flat surface, ideally a heavy steel plate or thick concrete, to pulverize a chunk to gravel size. Then either wrap the gravel in cloth or place it in a durable metal pan and crush it further with a rounded rock or hammer butt. Your goal: powder or coarse sand, with visible mineral grains released from the quartz matrix. Sieve the crushed material if possible. Using a kitchen strainer or 20-40 mesh classifier helps separate fine material that pans easily from coarse waste. Focus your panning on the -20 mesh fraction, where small gold particles concentrate. Add water and swirl gently to suspend the lighter silica sand while keeping heavier grains low. Gradually tip the pan and let lighter material wash away with each swirl. If the concentrate shows metallic flecks that remain despite swirling, and they lie flat or resist motion while everything else moves, those could be gold. Real gold appears as soft, yellow particles that don't float, shatter, or smear. It retains color under water and stays visible when you tilt the pan. If you can flatten a flake with a fingernail or knife tip, and it doesn't break, it's likely gold. You'll also find dense black or metallic residue. This could be magnetite, pyrite, or other sulfides. Run the magnet underneath the pan to isolate magnetic particles. What's left unmoved may include gold, galena, or non-magnetic sulfides like arsenopyrite. This concentrate tells you whether further processing is worth it. In productive zones, even a single pan test might show visible results: flakes, specks, or a yellow tail in the pan's bottom edge. But absence of gold doesn't mean absence of value. If the concentrate is rich in sulfides, the gold may be refractory, demanding lab analysis to confirm. Conversely, if everything washes away and no heavy residue remains, that quartz likely holds little more than silica and hope. The texture of quartz holds silent clues to its history, and whether that history includes gold. Seasoned prospectors read quartz not just for color or location, but for grain, pattern, and structure. 3 textures in particular, vuggy, sugary, and banded, deserve special attention because they often correlate with hydrothermal events capable of depositing gold. Vuggy quartz is the most obvious. These cavities, small hollows or voids, form when mineral-rich fluids deposit quartz but leave behind open spaces, or when earlier minerals dissolve out post-deposition. These voids sometimes retain druzy quartz crystals or oxide residues and can host visible gold, especially in high-temperature systems. In the field, a piece of vuggy quartz will sparkle at odd angles and feel irregular to the touch. Gold can plate along the walls of vugs or accumulate as wires or dendrites in sheltered cavities. These are rare but unmistakable signs when found. Sugary quartz, named for its granular appearance, forms when crystals grow rapidly or in brecciated zones where repeated fracturing occurred. The grains catch light differently than milky or massive quartz, often giving the rock a sparkly, granular surface. This texture commonly appears in shear zones or areas of strong fluid movement, where gold had multiple opportunities to enter and precipitate. Sugary quartz is often iron-stained along grain boundaries, especially where sulfides have weathered. If crushing sugary quartz yields black sand with brassy flecks, it's worth immediate follow-up. Banded quartz, especially when paired with alternating iron or dark mineral layers, suggests rhythmic fluid deposition, typically in epithermal or mesothermal systems. Each band represents a pulse of mineral-rich fluid, cooling and depositing as it moves through fractures. Fine banding, particularly when the bands are less than a millimeter thick and interlayered with sulfides, often signals the kind of episodic fluid activity that forms gold-bearing veins. In some cases, gold precipitates during specific phases, concentrating along distinct layers. Textural combinations are even more telling. A piece showing sugary texture near the surface, vuggy pockets deeper in, and banding across a fracture line reflects complex, long-term hydrothermal flow, exactly the scenario in which gold is most likely to have precipitated. These textures also dictate how gold can be recovered. Vugs may hold visible gold. Sugary quartz may require fine crushing. Banded samples may show gold bound in sulfide-rich bands. It's also worth noting that texture often degrades with weathering. Surface float may lose banding or vug sharpness, especially in arid zones where oxidation dominates. In such cases, freshly broken faces are essential. Always strike a test face if texture isn't obvious, because beneath a featureless rind may lie the structure that shifts your assessment. In fieldwork, crushing and panning reveal the surface story, but gold often hides deeper. That's when professional assays become necessary. Yet not every promising rock justifies the time and expense of lab testing. The decision to send a sample for fire assay or XRF hinges on practical thresholds. How much visible gold, sulfide density, or indirect evidence must be present to warrant formal confirmation? The traditional benchmark for assay consideration is a consistent presence of heavy, metallic concentrate after crushing and panning, even if no visible gold is seen. If repeated pans from different parts of the same vein or float yield a black or brassy concentrate that doesn't wash away and resists magnetic removal, the gold may be refractory, locked in sulfides, and an assay becomes the only way to confirm its value. In systems with visible gold, the bar is lower. Even a few unmistakable flakes in hand-sampled quartz justify assay, especially if found in multiple locations. A general rule of thumb: if you recover more than 0.1 gram from a single fist-sized rock via panning, that sample may exceed 20-30 grams per ton, G/T, a commercially significant grade, particularly for underground mining. But what if there's no visible gold? Then the decision shifts to sulfide content. Quartz samples with more than 5% sulfides by volume, especially arsenopyrite, are strong candidates. In field terms, if the crushed sample yields heavy residue that visibly alters a magnet's path and resists water separation, you're in potential assay territory. Color zoning, strong iron staining, and the presence of quartz textures linked to hydrothermal flow, like sugary or banded zones, further support this. Assay type matters too. Fire assays remain the gold standard for detecting total gold content, especially in sulfide-heavy samples. They're sensitive down to parts per billion and capable of detecting locked gold that visual methods miss. For initial field screening, portable XRF X-ray fluorescence devices can provide elemental readings, including arsenic, iron, and sulfur levels, indirect clues of auriferous sulfides. However, XRF struggles to detect gold directly unless present in high concentrations. It's also worth batching samples, sending multiple specimens from the same site with varied textures and sulfide levels. Labs can perform comparative analysis, and one high-grade result can validate further exploration. Across gold-bearing regions, faint scars in the landscape, collapsed adits, overgrown trenches, scattered quartz rubble, often mark abandoned opportunities. In many cases, these old diggings were never fully exploited. They operated under lower recovery efficiencies, lacked modern analytical tools, and discarded material that today could still yield viable gold. Recognizing and reevaluating these zones with a modern lens can transform overlooked spoil into productive ground. Tailings piles are the first place to start. In the 1800s and early 1900s, free milling gold was the only economically recoverable form. Anything not visible or easily separated by mercury or gravity methods was discarded. This means sulfide-rich or fine disseminated gold remained untouched. Today, with improved flotation, roasting, and cyanidation, many tailings show reprocessing potential. To evaluate tailings, begin with a pan sample. Even if no free gold appears, a persistent black or brassy residue, particularly one that includes non-magnetic metallic particles, can signal refractory material. If the pan result is promising, assay selected samples from different sections of the pile, noting variations in grain size and oxidation level. In some historic camps, tailings from the final years of operation carry higher grades than the ore that initially justified the mine. Old adits and trenches also reveal key structural clues. Exposed quartz veins, especially those with visible iron staining or sulfide streaks, may still be mineralized. Early miners often stopped work when grades dropped below a few ounces per ton, unaware that modern recovery could profitably extract much lower concentrations. Additionally, veins that pinch out on the surface may widen or enrich at depth, a common phenomenon in orogenic gold systems. Always cross-reference historic sites with public records. Many 19th century operations failed to document production data or abandoned claims during market downturns. These records, where available, often reveal vein orientations, past assay results, and even the names of shafts. Matching that historical geometry with modern GPS and mapping tools allows you to predict extensions or blind offshoots of the old system. Safety is a concern. Never enter old adits or unstable workings. Collapse risk, bad air, and hidden shafts are real dangers. Instead, focus on surface expressions, float trains, trench backfill, and exposed quartz remnants. Use a metal detector around dump edges to locate overlooked nuggets or heavily mineralized fragments. In many places, historic workings sit on public land or under unclaimed status. But don't assume access rights. Verify land status, mineral rights, and local regulations before sampling or removing material. Reclaiming forgotten ground can be lucrative, but it must be legal. Gold-bearing quartz is not distributed randomly. It clusters along ancient structural belts and within specific geological provinces where heat, pressure, and mineralized fluids once converged. Knowing where to focus reduces blind searching and aligns your efforts with centuries of documented success. Across continents, a handful of regions stand out as global hot zones for quartz-hosted gold, each shaped by a unique combination of tectonics and chemistry. The California Mother Lode is perhaps the most iconic. Stretching over 120 miles along the western Sierra Nevada, this belt hosts thousands of quartz veins emplaced along fault zones within metamorphic rock, especially slate and greenstone. These mesothermal veins, often iron-stained and fractured, yielded millions of ounces in the 19th century, and many were abandoned while still mineralized. The key diagnostic feature here is quartz hosted in a sheared slate or phyllite matrix, with limonite and pyrite remnants. In Western Australia, the Archean greenstone belts, particularly around Kalgoorlie and the Yilgarn Craton, are world-class. Here, quartz veins run through altered basalt and ultramafic rocks, often accompanied by chlorite, carbonate, and fuchsite alteration. These belts are known for both visible and refractory gold, often locked in arsenopyrite or fine pyrite. The alignment of quartz with regional shear zones is a critical vector in this terrain. Canada's Abitibi Greenstone Belt, straddling Ontario and Quebec, has produced over 170 million ounces of gold, mostly from quartz-carbonate veins in mafic volcanic rocks. These are classic orogenic systems where fault-bounded greenstones host quartz with varying sulfide loads. Visible gold, though rare, often occurs near fold hinges and fracture zones. The presence of sericite and iron staining in quartz here often signals economic potential. In South Africa, the Barberton Greenstone Belt, though overshadowed by the Witwatersrand Basin, is a historic source of quartz-hosted gold. Narrow veins within comatites and banded iron formations often host high-grade pockets, with visible gold sometimes associated with talc-rich or silicified zones. The combination of ancient crust and intense deformation makes this one of Earth's oldest and richest gold terrains. South America holds its own. In Brazil's Quadrilateral Ferro and along the Andean origin, quartz gold systems occur within both Precambrian shields and younger volcanic arcs. Especially notable are steeply dipping quartz veins in schistose or philitic host rocks, often iron-stained and sulfide-bearing. These veins may appear narrow on the surface, but widen at depth. Other notable zones include the Otago Schist Belt in New Zealand, where low-sulfide quartz veins run through metasediments. The Variscan belts of Europe, especially Brittany and the Iberian Massif, known for narrow but high-grade quartz veins. The Alaskan Tintina Gold Belt, where gold-bearing quartz is often associated with intrusive dikes and shear zones. While each region differs in host rock and structural context, common themes emerge. Quartz tied to faults or shear zones, surrounded by altered or reactive host rocks, and often stained by iron oxides or studded with sulfides. Understanding the macroscale location helps narrow your search, but on the ground, it's still about reading the terrain, especially where quartz appears in float trains or sudden surface blowouts. Scattered quartz boulders on a slope or in a creek bed might seem like random debris, but they can mark the surface signature of a hidden gold vein. Known as float trains, these linear patterns of displaced quartz fragments often trail away from buried sources, carried downhill by erosion or gravity. And when those float pieces exhibit iron staining, heavy sulfide content, or anomalous weight, they become directional clues, natural compasses pointing back to undiscovered bedrock veins. A quartz blowout is the starting signal. This term refers to an exposed patch of quartz rubble where erosion has revealed part of a vein, or where weathering has shattered vein material into angular chunks. These zones, typically found along ridge crests, fault intersections, or outcrop shoulders, represent either the surface termination of a vein or areas where intense weathering disintegrated the overlying rock. Often, blowouts coincide with visible iron oxide crusts or altered host rock, suggesting hydrothermal activity. From the blowout, float trains may descend for hundreds of meters downslope. In hilly or mountainous terrain, these fragments follow the path of least resistance, gravity, runoff channels, and soil movement. By mapping the location, size, and orientation of these quartz pieces, prospectors can walk the float upslope toward the source. This requires methodical gridding, marking float concentrations, noting color changes, and tracking mineral content. A key diagnostic here is float sorting. Higher-grade material, heavier or more iron-stained quartz, tends to settle closer to the source. Lighter, cleaner float travels farther. So, if a float train becomes less stained or lighter as you move downhill, you're likely walking away from the vein. Conversely, increasing sulfide flecks or a shift towards sugary or vuggy textures suggests proximity to the origin. In glaciated terrains or areas with complex erosion, float trains may be displaced laterally or downslope by hundreds of meters. That's where knowledge of local geomorphology comes into play. Prospectors use clues like striated bedrock, glacial movement direction, colluvial slope angles, or stream cut patterns to correct for float displacement. For instance, if boulders appear on a terrace well above the current stream, they likely originated from an upslope bench, not the channel. Don't ignore small fragments. In many cases, the float that carries gold isn't the massive white boulder but the rust-stained granular shard tucked into creek gravels or hillside loam. Sampling these small float pieces, crushing and panning them, can confirm whether they're carrying free gold, sulfides, or are just inert quartz. Where a float train seems to vanish, probe the soil. Shallow trenching or augering into red-stained ground beneath a terminal float boulder may reveal a buried vein. The appearance of angular, unrounded quartz chips in soil, especially if consistent over several meters, suggests you're close to in-place mineralization. In this case, it's not erosion you're following, but direct weathering from bedrock.